Hello, my RF and microwave engineers, designers, researchers. Welcome back to my series. This is Dr. Mohamed Nezami coming to you from Jerash, Jordan. I'm a freelance RF and microwave circuit designs, actives and passives. Today, we're going to cover the second part of the slotted waveguide antenna array design and 3D modeling. You may recall last time, first of all, before we do that, a little marketing message here. I'm a freelance, like I said, designer, offshore designs. If you have any RF active or passive boards that you need for your system, please don't hesitate to reach out to me at this email right here. I work with you from concept to specifications to system architecture, system modeling, and then on to producing schematics and BCBs. And I turn in BCB fab files to you along with bill of material and work with you on the BCBA and even work either remote or on-site with your engineers for testing and verifications and system integration. Okay, so today I'm gonna continue what I started. As you know, last time I have introduced the slotted waveguide antenna concept, showing you, starting out illustrating a single slot and how the physics behaves for it, how to design one, and so forth on a concept level. And it was then that we introduced the concept of a slotted waveguide array where we have a bunch of rectangular waveguides, and then we put slots at some predetermined spaces with certain dimensions in them, and then we feed them all in a predetermined engineered way, and then we can produce the complete aperture that is used for systems such as radar and satellite communications. So last time, if you recall, last time, if you recall, so today we're gonna, in a minute, we're gonna go further and design a 16 slot antenna section. But before we do that, let's just recall what we did last time. Last time we came and said, okay, here's a waveguide that we have where we excited it on one side, on this side, and put a slot in here and said, let's see how this behaves. Of course, this slot is offsetted from the center at a distance, which I did not show you yet at the time how we calculated that distance from the center line of the broad wall. But today we're going to do that. I'll show you some computer code that will generate that. And then we looked at this as an antenna, basically where the gain, we can see the gain, okay, and then see the 3D gain that this produces, okay? And you can see that it's wide bandwidth because single element. And then, of course, we showed how the E field and the current behaves on this. So we see that how the E field propagates into the waveguide from one port to another port, and how it radiates through the slot, and that's what makes that. So for those of you that did not watch the part one, please go back and review part one, okay? So today, what we're going to do, we're going to go further, and obviously a single slot is not going to make a good antenna. Let me just hide this airbox. What we need to do more than one slot. So we're going to go today is that basically repeating the slot. Okay, the way I created this slot is you create a rectangular solid model that has the same thickness as the waveguide ceiling, and you subtract it. So what I basically do here is I subtract the this slot from the from this piece of metal here that is being hollowed by an inside air. Okay, so what we're going to do today is we're going to come back and, for instance, create another slot if you want, and then we're just going to offset that in the z direction by a quarter wavelength, which is the distance between, I mean, a half wavelength, waveguide half wavelength, which is basically the distance between the slots. And also, we're going to alternate the offset from the center line. But I'm going to just put a negative right now on this one, and you can see how this. So what we did is I repeated this and then basically made an offset. And now we can again subtract this from the solid top part of the waveguide. Okay, and that basically produces how we can repeat this to get this type of work. So today, what we're going to do is we're going to look at how this behaves. And this is 16 slots, okay? And the reason I want to build this is because I want to build actually one of these here. We've got 2, 4, 6, 8, 10, 12, 14. This is a 14, but in my case, I want to build 16. I'm going to stack number of them and then taper the waveguide length down like this so that I can get a circular beam like this, very narrow beam, okay? And then I'm going to build another waveguide behind that feeds in these the RF signal to all of these stacks, slotted stacks via another waveguide behind with inclined slots. So let's just so now let's just review how we're going to do this. How we're going to design this 16 slot element. Okay. Let's just recall from part 1 that slotted waveguide is nothing but a waveguide where you feed the signal on one side, shorted on the other side, and then we basically throw in a bunch of slots, either square slots or rounded, it doesn't matter, either one. And then the distances between them is a half waveguide length. And then the distance between the center of the last slot and the shorted wall is a quarter wavelength. Or in my case, I use 3 quarter wavelengths. You can do whatever odd number of quarter wavelengths in here. It will all work, okay? And then likewise, at the beginning, from the input, the illumination input, the input here, to the center of the first one is also another quarter wavelength. And the reason we do this here is the distance 1/2 wavelength between the slots and then a quarter wavelength between the input to the center of the first one is basically to try to couple in the E field of the TE10 at these distances where it's maximum. And we went through that last time, and I do urge you to go back to part 1 and review that. So today, this is the first example. We're going to take 1/16 slot waveguide antenna array, as you see here. Now, the calculation, like I said last time, we use Elliott equations to design the slots. And so what I did is I wrote a little, let's look at the example that we're going to do today. We're going to start out with a WR90 waveguide, which has the dimensions that is determined in here. Okay, this is a standard waveguide. And we're going to try to design this antenna at 10.3 gigahertz, which is the weather radar systems, okay? Where that's the middle of the X band. Now, as you know, last time I told you that these because the distances between the slots is a half waveguide length, and the length of the slot is actually a free space half wavelength. This system is resonance system, meaning that it will operate optimally at a single frequency, and then very fast it will deteriorate. That's why these systems are held primarily for systems that are on the order of, say, 200 to 300 megahertz at most. Otherwise, you would have to go to non-resonant slotted waveguide antennas, which are more complex, and they have to be fed from the side. They have to have load termination on the other side. So, which is anyway, so the number of slots is going to be 16. So we start out crunching these numbers in here, and I'll show you there's a MATLAB script that I did, which coincidentally, by the way, will be posted in the comments or in the video description. If it doesn't fit in the video description, you'll find it in the first comment, okay? So starting out with just a TE10 waveguide equations, like the cutoff wavelength is twice the broad wall distance, the free space wavelength is the speed of light divided by frequency. The length of the waveguide wavelength is defined by this equation, which is a standard. And I come up with all these numbers in here. So this at 10.3 gigahertz, the wavelength in free space is about 29.12 millimeters. The waveguide wavelength is 37.78 millimeters. And then of course, from that, now the first dimension that can fall out of this, according to trying to find these dimensions in here to determine where the slots should be placed at, the quarter wavelength and the half wavelength, waveguide wavelength. So in that case, it turns out that the slot spacing is going to be 18.89 millimeters. The slot length will be at 14.56 millimeters, which is half of this value here, okay? Now, the total length of the waveguide, of course, is going to be, if you look at this, the total wavelength is, you've got a quarter wavelength in here, a quarter wavelength in here, so that's half. And you get, depending on the number of slots in here, so n minus 1 times the this value here, 1/2 of a wavelength, that's going to be the total length. If you happen to increase this to another odd multiples of quarter wavelengths, then you just add that twice. So, and that's what you see in here. So n minus 1, the number of slots minus 1 times the spacing between them, plus 3/4 of a wavelength, plus 3/4 wavelength, that's the beginning, the end, which is equal to 311.685 millimeters, okay? The slot width, I used Elliott equation, Elliott references. I've shown them in the Dr. Elliott's publications on this in part 1. Go back and watch that. I use this equation in here, okay? So basically, when I did this in the, when I constructed this system in here, I parameterized the dimensions in the HFSS to accommodate this, so that I can recycle this design at other frequencies as well. So as you can see here, like the waveguide, total waveguide length is equal to this equation in here. The slot width is equal to this equation in here. And of course, the slot length and the slot spacing is also programs in here, okay? All right. So this is the code, okay? So basically, I have this code that I wrote in MATLAB, okay? And it's pretty straightforward. These are all standard equations that I put in the script, and this is what comes out. Again, do the same thing for the other dimensions. There are some formulas for the expected gain and the beam width, okay? And you can utilize those to predict ahead of time what those values should be in theory. And then, of course, now, how do we find the most important thing is now, so we know the slots are 16, and we know that they alternate at a certain distance offset from the center line of the broad wall. But how do you determine this distance in here? And that's very important, crucial design. And that has to do with by trying to model these slots as parallel loads across the input. And the equation is right here. Okay, so the distance is basically equal to this here, which is A over pi, the broad wall length width over pi times this value in here. G here is this equation in here. Okay, and these are derived, if you are interested in seeing how we came about with these are derived by Mr. Elia in his references. Now the references are listed in my first video of this series. Okay, so basically, if you look at this, it's really the distance is a function of the waveguide itself. This is, by the way, this is for uniform distributed offsets, meaning the offsets are equal for all of these. Now, with that, that means it's a rectangular window of excitation, and therefore the sine x over x, or the radiation pattern, is going to have a side lobe of exactly 13 dB, just like you would expect, because it's non-window. This is not tapered. So this is pretty easy. I'm going to start with this, and then I'll come back and do a Chebyshev tapered one. And that's why I solved. So the first one is we assume that we have a bunch of 16 equal excitations on all of these slots. Okay, and then we solve these equations, and this equation should give me this number in here, which is this right here. Okay, so these GNs in here, what I do, of course, is you take A1, is you sum them, which is 16, and that's 1 over 16, so that you normalize you distribute the overall power excitation is equal to the input, which in this case is normalized to 1. So, and this here is actually the actual offset, which the diagram in here made it P, which is this one here, XN uniform. So that's a 2.3 millimeter. And that's what I have. If you look at these, at the design properties in here, so that's the slot offset is 2.3, and that's equal to all of these slots. So we've got these slots are put in, and then we subtract them from the top of this the aluminum, but every one of these is actually offsetted by the number, which is 2.3 millimeters. Okay, so that's for uniformly spaced. Okay, now but in a lot of cases we really need to taper the beam, the radiation pattern, and that's where we have uniformly distributed, and that's where we use either Dolph-Chebyshev windowing or Taylor or binomial. So what I did in here, I said, let's use a MATLAB function, which is basically Chebyshev wind, which synthesizes a Chebyshev window with a certain length, which is n, 16 in this case, and then the side lobe level ratio, which in this case in here, I started out with 40 dB. Okay, and of course you normalize these, and you calculate based on this equation, which is this here. Okay, so all this equation gives you the distances are as a function of GNs, and GNs, of course, they're all proportional to the window value, which is here. This is the window values in here. So when you solve this, you get basically 16 slots, 16 coefficients that are they're basically mirror image. Half of them, 8 of them, are equal to the other half. So we've got 8 of them here and 8 of them here, and that's because the windowing function is symmetrical on both sides. So if it's a length 16 And that's from that we can solve for xn's, and these are the lengths. And you can see that this waveguide would have to be maximum distance offsetted at the center, where two distances, and then it tapers to the end where it's 0.93. Okay. And then, of course, now what I could do in a lot of cases, you don't need 40 dB of side lobe. That's too much, because the trade-off is that it really widens the main beam as a trade-off. I said, no, I want the ratio of the side lobe level to be 20 dB in this case. And you get this here. Okay, this is basically your window, and these are my distances. Okay. All right, so we have this design in here. So where I started, I plugged all these equations, okay, and this is for uniform distribution. The slot offset is equal for all of them. In this case, I solved it to be 2.3 millimeters, and that's right here. That's from this equation here, okay? So once I construct this, I run the HFSS, and this is basically the pattern I get with a gain of 19.2 dB out of this, okay? And as you can see, it's right here, 19.2 dB. That's the radiation pattern, the antenna pattern. And if you look at the 3D pattern at a different observation angles, this is how it looks like. Of course, the side lobe levels is high in here. This is only 13 dB down. And in the next session, or the session after, we will revisit this, the same design. We'll do tapering so that we can bring down these side lobes in here. Okay, now if you look at the three, minus 180 to plus 80, 180 radiation pattern, you end up with this exactly here. Okay, and so the gain is 19.2, and if you can see that the difference between these two numbers gives you the side lobe level, which is 13, 14 dB now. Of course, you got the backfiring in here because you don't have any reflector on this or any backplane ground. If you sweep as a function of frequency, as you might expect, it's designed for 10.3, and it's really narrow. It's only like you can get this flat gain of 19 dB only over, let's see, 10.25 to 10.5 almost. So it's 250 megahertz, okay? The return loss right now without any optimization looks like this. So it's not pretty excellent, but we have an overshoot in here in the middle that we have to reduce. So that means, of course, now the design is not optimized right now. So it's really this is a fair shot at it. So what we would do next is we're gonna sweep and optimize this so we can improve the input return loss without impacting the radiation pattern. Okay. So next week, what I'm going to do, I'm going to take one of these and feed it in the middle with another waveguide. And the other waveguide is going to be, has slots that are inclined, and they would feed the signal in the back of the waveguide. So the slots, the radiation slots, are on top. And then on the bottom of that waveguide, we've got another waveguide that is a 90-degree placed orthogonal at the bottom, and then it has another slot in the bottom that will radiate from the feed to this waveguide, because obviously this one here, I'm feeding the signal from this side. I'm going to replace that with actually this mechanism in here, because that's how you would have it in actual systems. Okay, so let's go back and now let's see. This is the MATLAB code, of course, that I wrote to do all of these equations. And these equations are pretty simple. So, and of course, this is the output of the code, and you get basically the final thing for for tapered ones is you get the slot number and you get the coefficient and then the offset placement of the slots. And of course, if you come in here in the middle, you notice these two are equal, slot 8 and 9. And then of course it tapers to the sides of each side. So basically we feed right here in the middle where the signal splits equally between the right and the left. And that's what we're going to do next time. Okay. And of course, you can go back to the MATLAB windowing function. Right now, I'm using this here, this object, which creates a Chebyshev window. And all you need to feed it with is just the slot number and the ratio of the side lobe level. And it will give you the basically these coefficients in here, these coefficients. Okay, so let's go back to the design in here. So first thing is, of course, you can look at the gain in here. Here's the gain, and it calculates the gain. Of course, it gives you that's 19.2 dBs. Okay, and you can see the gain with this polar plot in here as well. And it's 19.2 at that frequency, 10.3 gigahertz. The 3D gain pattern is this, of course. You get this, okay? And it's pretty sharp, as you can see, 10-degree wide. But we need to knock down these here. And of course, you need to reduce the back level because obviously that gives you false targets. Okay, so this is basically this here. So what we're interested is just this here. This would be the pattern that you're looking at, okay? All right, let's see. The S parameters, like I said, we have an undesired little reflection in here that we need. So we need to optimize the slots a little bit to get them. Of course, frequency as a function, the gain as a function of frequency, swept it, and it looks pretty much like I told you. We can look at the E field in here, and even actually, let's do animation and see how this behaves. Okay, it's going to take a moment. Okay, so you can see here now that the signal propagates in here until it hits the first slot. Let's see if you can see the slots. You can see the slots in here. Okay, so you can see how the signal at every slot, how it leaks out, basically. Of course, the placement of these in an alternating pattern around the center. Of course, this distance in here is the last. This is the last slot, and this distance in here from the short, this short in here, this cover, this here, this is a short metal. What happens? The signal will reflect back in phase and come back to the first, to the last slot number 16 in here. Okay. All right. So what we're going to do next is giving this how it is. What I'm going to do is basically we're going to come in and say, okay, we have this. So we're going to go in and feed this waveguide right in the middle with another waveguide that is perpendicular to this, to the radiating one. And that's basically the like I showed in this here, is because what we want to do eventually is build it like this, and then we're going to extend this waveguide to go further and feed a stack of these. We're going to stack a whole number of these. All right. Okay, well, this really so this really what I have for this part. So we're gonna go next and feed the signal with a coupling waveguide, so that we make it 2 layers of waveguides. Okay, ladies and gentlemen, this is Dr. Mohamed Nezami. Thank you very much for watching. Please, like I told you, please go ahead and subscribe to my channel, please, and give me any comments that you may have. Okay, so